The physical significance of criterion of chemical equilibrium is being explained with chemical potential with respect to A and B reactants. So, when mu A is greater than mu B, the reaction goes to the forward side. When mu A is less than mu B, the reaction goes to the reverse side. When mu A is equal to mu B, the slope of the curve is said to be 0. The physical significance of the criterion of chemical equilibrium is also given by the slope which has been plotted. The slope has been plotted with Gibbs free energy G power T and extent of reaction epsilon. So, when Gibbs free energy is less than 0, then the slope of the curve is said to be in the reverse direction. When Gibbs free energy is greater than 0, the slope of the curve and the reaction is said to be in the forward direction. When Gibbs free energy is equal to the extent of the reaction, then the slope of the curve is said to be 0. Next, we will talk about the equilibrium constant. We are going to derive an expression for equilibrium constant. Let chemical reaction where A moles of A react with B moles of B, which gives L moles of L and M moles of M, then the equilibrium constant K or Ka in terms of activities of the reactants and products are given by the expression K is equal to Ka, which is equal to A suffix L power L, A suffix M power M divided by A suffix A power A and B, A power B suffix B power B is equal to pi Ai power Vi, where Ai is the activity of the component I of the reaction mixture and small Vi is said to be the stoichiometric number of I. So, we know that the activity coefficient of the reactant is given by the fugacity expression, which is Ai is equal to Fi bar divided by Fi naught, and already we know that the expression for chemical equilibrium constant is said to be K is equal to pi Fi bar divided by Fi naught to the power Vi as equation 2. Now, we are substituting this value into this expression. We get pi into Fi bar power Vi. This we are naming it as equation 3, and this whole expression is considered to be Kf, where Kf is the equilibrium constant in terms of fugacity of the components. We know that Fi bar is equal to Phi bar into Pi bar. So, this expression we are substituting it in equation 3. We get pi into Phi into Pi bar to the power Vi, where this is said to be the whole expression. And for liquids and solids, equilibrium constant K and Kf are not numerically equal. So, the equilibrium constant in terms of partial pressure Kp is given by Kp is equal to pi into Pi bar power Vi. This expression is said to be equation 5, and we already know that the fugacity is said to be in terms of Phi into partial pressure Pi bar. So, this we are substituting it in equation 5. We get K is equal to Kf, which is equal to pi into Phi into partial pressure Pi power Vi. This expression can be also deduced to K is equal to Kf, which is equal to the whole expression is taken as Kphi and Pi is taken as Kp. This is said to be equation 6. Since it is an ideal gas, the system here is said to be having the ideal gas, then Kphi is equal to 1. Hence, K is equal to Kf is equal to Kp. This equilibrium constant is explained with two types of reactions occurring with water. where 2H2 gives 2H2 plus O2 or H2O gives H2 plus half O2. So, this equilibrium constant expression of this two particular reaction can be written as K dash is equal to AH2 power 2 AO2 power 1 divided by AH2O power 2, and K double dash for this particular reaction is given by AH2 power 1 AO2 power half divided by AH2O power 1. So, these two reactions with the terms K dash and K double dash can be written as K dash power half is equal to K double dash. Equilibrium constant and standard free energy change for criteria concept equation. So, we are going to derive the equilibrium constant for standard free energy change and criteria concept. We are taking an equation for the criterion concept already, which has been taken, where L mu L plus M mu M minus A mu A plus B mu B is equal to 0 as equation 1, and we already know that the chemical potential of the component in equilibrium state is said to be mu I is equal to RT ln Fi bar plus C. This is considered as equation 2, and mu I is equal to RT ln Fi naught plus C, and this is considered as equation 3. Hence, the standard state is said to be depending on in terms of temperature on both sides. We are subtracting the equation 2 minus 3. We get mu I minus mu I naught is equal to RT ln Fi bar minus RT ln Fi naught. We are taking this mu I and mu naught to the other side. We get the equation as mu I naught plus RT ln Fi bar divided by Fi naught, which is equal to mu I naught plus RT ln AI, and this is considered as equation 4. Now, we need to expand the equation and we have to substitute in the place of mu I this following expression. So, in the equation as which is given in equation 1, we substitute, we get L mu L naught plus RT ln AL plus M mu M naught plus RT ln AM minus A mu A naught plus RT ln A plus B mu naught B plus RT AB, which is equal to 0. Now, we need to multiply the terms and subtract. So, we get the whole entire equation as L mu L naught plus M mu M naught minus A mu A naught plus B mu B naught plus RT ln AL plus RT ln AM minus RT ln A plus RT ln AB, which is equal to 0. If we multiply the terms and expand these terms, we get the expression as L mu L naught plus M mu M naught minus A mu A naught plus B mu B naught plus RT ln AL power L AM power M minus RT ln A power A into A power B divided by A power B is equal to 0. This we are taking it as equation 5, and now we are taking the common terms to one side and the RT terms to the other side. We get L mu L naught plus M mu M naught minus A mu A naught plus B mu B naught is equal to minus RT ln AL power L AM power M divided by A power B, which is equation 6. So, the entire term on summation we can write it as summation of mu I naught Vi is equal to minus RT ln A power L A power M divided by A power B, and delta G naught is equal to minus RT ln K. This is said to be the equilibrium constant. Feasibility of the reaction. So, the feasibility of the reaction is explained by when equilibrium is favorable or not, or by searching catalyst and conditions to proceed the reaction. And there are certain conditions which satisfy the feasibility of the reaction. So, if the reaction is not feasible, means there is no use of investigation about the rate of the reaction. Up to few extent, the chemical reactants without contamination will have tendency to proceed, and this is considered only at infinite small. And when equilibrium constant and standard free energy gives necessary information on the possibility of the reaction, the feasibility of the reaction is possible. This is explained with the water reaction, where water is in the gaseous form, which gives hydrogen and half oxygen, and to some extent this reaction proceeds under atmospheric temperature and pressure. The standard free energy and the value of K is said to be K is equal 1 into 10 power minus 4 at the temperature 298 Kelvin. At 298 Kelvin. Hence, the extent of decomposition of water vapor which is taking place in this reaction is said to be in the infinite small and equilibrium. Therefore, the reaction has no thermodynamic feasibility, we can say, and the Gibbs free energy, when it is equal to 0, then the equilibrium constant is said to be 1. When Gibbs free energy is said to be negative, the equilibrium constant is said to be greater than 1, and when Gibbs free energy is said to be increased or positive, then the reaction is said to be increasing. The equilibrium constant and standard free energy also explains these types of conditions. When Gibbs free energy is greater than 0, then the reaction is said to be promising, and when 0 less than Gibbs free energy, which is less than 40,000 kilojoules per kilomole, maybe the reaction is possible and needs to have further study. And if Gibbs free energy is greater than 40,000 kilojoules per kilomole, then the reaction is said to be unfavorable. Now, we will talk about the effect of temperature on equilibrium constant, and this concept is explained by the principle called as Le Chatelier's principle. The Le Chatelier's principle explains the effect of operating variables on equilibrium, which can be qualitatively explained by this principle. So, when the principle says that when the system is disturbed, the disturbed system itself tends to minimize the effect of disturbance. Hence, there are two criteria which satisfies the Le Chatelier's principle with respect to heat. So, when the heat of the reaction increases, then the equilibrium state is shifted to absorption of heat and the reaction is said to be endothermic. When the reaction or the heat is decreased, then the reaction is said to liberate heat and the reaction is said to undergo exothermic reaction. Now, we will derive the Van 't Hoff equation, which explains the effect of temperature on equilibrium constant. The relationship of equilibrium constant is qualitatively expressed by the equation called as Van 't Hoff equation or the standard free energy equation, which is given by del G naught is equal to minus RT ln K. So, this is said to be equation 1. For a single species, the effect of temperature on its free energy is predicted by Gibbs-Helmholtz equation, which is given by dou Gi by T divided by dou T with respect to P is equal to minus Hi divided by T squared, and this is said to be equation 2. For the substance in standard state, above equation can be written as this. Above equation 2 can be written as dgi naught by t divided by dt is equal to minus hi naught divided by t squared. So, we have removed the partial derivative as the standard free energy by virtue of its definition of standard state, and this is said to be equation 3, and overall the equation can be written as differential of summation of Vi Gi naught divided by T by dt, which is equal to minus summation of Vi Hi naught divided by T squared, and this is said to be equation 4. The standard free energy of reaction and standard heat of reaction are related to free energy and enthalpy of individual species, which is given by delta G naught is equal to sigma Vi Gi naught and delta H naught is equal to sigma Vi Hi naught, and equation 4 we get by dividing the equations on both sides by R. We get the following equation as differential delta G naught divided by RT divided by dt is equal to minus del H naught divided by RT squared, and this is named as equation 5, and this is the expression for Van 't Hoff equation. When we substitute the following equation with 5, we get d ln k divided by dt, which is equal to del H naught divided by RT squared, and this is the main equation for Van 't Hoff equation. And if the del H is said to be in the standard heat of reaction, then the equation changes to ln k divided by k1, which is equal to minus del H naught divided by R 1 minus T and 1 minus T1, and this is said to be equation 7. So, this equation applies when there are two different temperatures and two equilibrium constants are given. The next topic is about how to evaluate the equilibrium constants. So, there are three methods to evaluate the equilibrium constant. The first method is it can be calculated from experimental measured composition of equilibrium mixture. So, the equation is given by K is equal to Ka, which is equal to Al power L, Am power M divided by A power A power B, which is equal to pi Ai Vi. And the second method is about standard heat of reaction at one temperature and one value for equilibrium constant, that is determined by direct experimental measurements. And the third one is no direct experimental measurements for the equilibrium constant, and it is this method is the mostly used method. Now we will see some of the problems based on chemical reaction equilibrium. The first problem is the standard heat of reaction formation and the standard free energy of formation of ammonia at 298 Kelvin are minus 46,100 joule per mole and minus 16,500 joule per mole respectively. Calculate the equilibrium constant for the reaction. The reaction is given as N2 plus 3H2 gives 2NH3 at 500 Kelvin, assuming that the standard heat of reaction is constant in the temperature range 298 to 500 Kelvin. So, now the standard free energy of reaction is constant in the temperature range at 298 to 500 Kelvin. So, the equation we can write as del G naught is equal to summation of the modulus of the Vi into del Gi power J naught minus summation of modulus of Vi delta G naught I comma J for reactants. The second summation yields 0 as the free energy of the formation of elements are said to be 0. And now the product, the standard free energy of the product is given by 2 into minus 16,500. When you multiply it, we get the answer as minus 33,000 joule per mole. For the product, the standard free energy equation is said to be minus RT ln K. When we substitute the delta G naught value, and R is 8.314 and temperature, which is already given in the problem, which is said to be 298 Kelvin. When we substitute, we get the answer as 13.31, and therefore when we take the ln of this value, we get 6.0895 into 10 power 5, and this is said to be the standard heat of reaction at 298 Kelvin, which is said to be 2 into minus 46,100, and the standard heat of reaction is said to be minus 92,200 joule per mole, and this is assumed constant within the temperature range. So we can substitute the Van 't Hoff equation where two different equilibrium constant and two different temperatures are given. When we substitute the value, we get ln K divided by 6.085 into 10 power 5, which is equal to 92,200 divided by 8.314. We get the temperature as 1 divided by 500 minus 1 divided by 298. We get minus 15.0344, and the equilibrium constant value at 500 Kelvin is said to be K is equal 0.8. The second problem is, in the synthesis of ammonia, stoichiometric amounts of nitrogen and hydrogen are sent to a reactor where the following reaction occurs. So this is the reaction. N2 plus 3H2 gives 2NH3. The equilibrium constant for the reaction at 675 Kelvin may be taken equal to 2 into 10 power minus 4. So there are two subdivisions given which has to be calculated. One is to determine the percentage conversion of nitrogen to ammonia at 675 Kelvin and 20 bar. The other subdivision is what would be the conversion at 675 Kelvin and 200 bar. So we are taking the basis as 1 mole of nitrogen and 3 mole of hydrogen, which are said to be in the reactant mixture. We are considering epsilon to be the extent of reaction. So the moles of various species at equilibrium, the equation is Ni is equal to Ni naught plus Vi epsilon. Then the moles of nitrogen, hydrogen and ammonia at equilibrium are 1 minus epsilon and 3 minus 3 epsilon plus 2 epsilon. So the total moles of equilibrium is said to be 4 minus 2 epsilon. The mole fraction of nitrogen, hydrogen and ammonia are said to be 1 minus epsilon, 4 minus 2 epsilon, and 3 into 1 minus epsilon divided by 4 minus 2 epsilon, and 2 epsilon divided by 4 minus 2 epsilon. The sum of the stoichiometric number for the entire equation is small v is equal to 2 minus 1 minus 3, which is equal to minus 2. We know that the equilibrium constant is said to be Ky is equal to K by Kphi into P power minus V, and this can be written as Kp squared while simplification. In arriving at the result of ideal gas behavior, we are taking the Kphi value as said to be 1, and so we get the necessary relation for the equilibrium constant for that particular reaction of ammonia to be 2 epsilon divided by 4 minus 2 epsilon the whole squared, minus 2 epsilon divided by 4 minus 2 epsilon the whole square divided by 1 minus epsilon divided by 4 minus 2 epsilon, and 3 into 1 minus epsilon divided by 4 minus 2 epsilon the whole cube, which is equal to 2 into 10 power minus 4 p squared. So simplifying the equation, we get 4 epsilon squared into 4 minus 2 epsilon the whole squared divided by 27 into 1 minus epsilon the whole whole power 4, which is equal to 2 into 10 power minus 4 p squared. This equation can be further simplified to epsilon 4 minus 2 epsilon divided by 1 minus epsilon the whole squared is equal to 3.6742 into 10 power minus 2 p. This 27, when it goes to the other side, we get this answer. So now we are going to calculate for different pressures. So the first pressure which is given in the problem is 20 bar. We are going to substitute 20 bar in the place of P. We get epsilon into 4 minus 2 epsilon divided by 1 minus epsilon the whole squared is equal to 0.735, and we are expanding this equation. We get 2.734 epsilon squared minus 5.4697 epsilon plus 0.73485 is equal to 0, and the value of epsilon is said to be 0.1448, and this is said to be the fractional conversion of n, and the fractional conversion of n can be written with the equation Z is equal to modulus of Vi epsilon divided by Ni naught. So in the place of epsilon we are substituting the value as 0.1448, and the present of value we get the answer as 14.48%. Now we are going to substitute the value of P is equal to 200 in this equation. We get epsilon into 4 minus 2 epsilon divided by 1 minus epsilon the whole squared, which is equal to 7.3485. We are expanding this equation. On expanding we get 9.348 epsilon squared minus 18.697 epsilon plus 7.3485 is equal to 0, and the value of epsilon is said to be 0.5375, and the conversion of nitrogen is said to be 53.75%. So next we will see the problem based on the presence of inert material. So this problem has the expression which involves the value of n. So we have an expression as K is equal to K phi Ky P power V, and this, on rearranging this equation, we get Ky is equal to K divided by K phi P power minus V, and this we are naming it as equation 2. So Ky in the above equation may be written as Ky is equal to phi into Ni divided by n power Vi, and this is equation 3, where I is said to be the species taking part in the reaction and Ni is said to be the number of moles, and n represents total number of moles in the reaction, and n is equal to sigma of Ni plus n capital I, where the presence of inert material takes place, and this is said to be equation 4. We have already derived this expression in the stoichiometric and the extent of the reaction, and we are combining equation 2 and 3. While combining the equation 2 and 3, we get pi into Ni by n power Vi, which is equal to capital N power minus V pi Ni Vi, which is equal to, we are substituting this in the value here, we get K divided by K phi P minus V. K is equal to K divided by K phi into P power minus V. So any change in the reaction increases in the right hand side. We get pi into Ni power Vi, which is equal to K divided by K phi into N by. Now we are going to see a problem based on the inert material. The standard heat of formation of mixture of 1 mole of CO and 1 mole of water vapor is undergoing the water gas shift reaction at a temperature of 1100 Kelvin and pressure of 1 bar, and the reaction is said to be carbon monoxide plus water gives carbon dioxide plus hydrogen, where the equilibrium constant for a reaction is K equal to 1, and assuming the gas as a mixture behaves ideally, we have two different subdivisions which has to be calculated. One is the fractional dissociation of steam, the other one is fractional dissociation of steam if the reactant stream is diluted with 2 moles of nitrogen. So we are taking the tabulation of the given datas. We are listing the components carbon monoxide, water, carbon dioxide and hydrogen. We are calculating small vi for the reaction. So this is said to be -1 for carbon monoxide, water for -1 for water, and +1 for carbon dioxide, and hydrogen as +1. We calculate Ni0, which is 1100, and the summation of Ni0 is said to be 2. The values of the mole fraction of Yi is said to be 1 minus epsilon divided by 2, 1 minus epsilon divided by 2 for water, and epsilon by 2 for carbon dioxide, and epsilon by 2 for hydrogen. We get the equilibrium constant as Ky is equal to 1, which is equal to, the equilibrium constant equation is mole fraction of carbon dioxide and mole fraction of hydrogen and mole fraction of carbon monoxide and water. This is product divided by reactant, and we have to substitute the respective values for the components. We get epsilon divided by 2 into epsilon divided by 2 divided by 1 minus epsilon divided by 2, 1 minus epsilon divided by 2. We get the equation as epsilon squared divided by 1 minus epsilon the whole squared. The value of epsilon is said to be epsilon is equal to 0.5, and the fractional conversion is said to be Z is equal to modulus of Vi into epsilon divided by Ni0. Substituting the respective values, we get 0.5 as the value, and the fractional steam conversion is said to be 50%. Now we have to calculate for the next one, because already here it is given when nitrogen is added 2 moles. So we are listing the components of the reaction: carbon monoxide, water, carbon dioxide, hydrogen, and nitrogen is also added. So we are also calculating Vi for the reaction. We are also calculating the Ni0 for the above reaction. So the summation of the reaction, we get 4 moles, and here we are calculating the mole fraction of the following components. They are 1 minus epsilon divided by 4, 1 minus epsilon divided by 4, epsilon divided by 4, and epsilon divided by 4. Now we have to calculate the equilibrium constant, which is Ky is equal to 1 minus the product divided by reactant. We are substituting the values of the product and reactant. We get this equation as epsilon divided by 4 into epsilon divided by 4 divided by 1 minus epsilon divided by 4 into 1 minus epsilon divided by 5. Simplifying this equation, we get epsilon squared divided by 1 minus epsilon squared. The fractional conversion of the water vapor is 50%.